So, hello. So, today we will define the Jones polynomial. So I think this is the second section. The Jones polynomial. So the goal is to define an isotopy invariant of oriented links, which is a Laurent polynomial. So we begin by defining what is called the bracket polynomial. The bracket polynomial. Okay, so consider a link diagram D. Now, if you have a crossing of the diagram, it may be split in two ways. So consider, so we have, so the diagram D, so you consider a crossing inside the diagram. So we can split into ways A and B as follow. So first, so we can smooth it like this or like this. So, and if we do this, we obtain two other link diagrams which I denote by dA and dB. dA will be this one. And this diagram, they coincide with the outside a disk around the crossing. Okay. And as you can see, the number of crossing so of DI and DB, they have one crossing less than okay. So now what we want to do, we want to split all the crossing. So by a state of D, I mean a map, let's call it S, from the set of crossing of D to the set into letter A and B. Okay. So if you have a link diagram with n crossings as, so how many states? 2 to the n. The n states. Okay. So So now, if you have a state of a diagram D, to any state S of D is associated a family, let's call it ds, of what? Of non-intersecting circles in the plane. And how do we obtain this family of circle? It is obtained by splitting the crossings according to their states. Okay, so let's see an example of this. So I consider the trefoil. Okay, so I have the trefoil, and I consider a state. So to each crossing, I have a letter. For example, for this one is A, B, B. Okay, so now, so if I D is a diagram here, S is a state, we obtain that ds. So we need to split the crossing according to the state. So in state A, so this one is B, so B is like this. This one is B, so it is like this. And this one is A, so it will be like this. So here we obtain two circles. I recall that we have this rule, A, this, and B gives this. And so using this rule, we obtain this system of a circle. Okay. Okay, so now we use, we define, so for a link diagram D, we define the following. It is a sum on the state of the diagram of the following: A to the alpha S, B to the beta S, C to the gamma S minus 1. So this is a polynomial in 3 variables, A, B, C. And here, I need to define the number alpha S, beta S, and gamma S. So alpha S is the number of crossing in state A. So this is the number of crossings in state A. Beta S is the number of crossings in state B. And then gamma S is what? Is the number of circles of ds. So, so the plane isotopies does not change the crossing, so we have that D is invariant under plane isotopies. Okay, so let's see an example how to compute D. So example. Let us consider D to be the diagram of the uplink. Okay. So there is 4 states for this diagram. Okay. So we can, so AA, AB, BA, and BB. Okay, these are the 4 states. Now, we compute the system of circle for each state. So here, so here. So here, this gives this one. Here, this gives the opposite. So and this one gives okay. So here we compute the number for each state. Okay. For the first state, there is 2 crossings in state A, 0 crossing in state B, and there is 2 circles. Here, 1, 1, 1. Here, 1 for A, 1 for B, 1 circle. 0 for A, 2 for B, 2 circles. And then what you obtain, this number D, so it is A2, B0, C1 plus A1, B1, C0 plus A1, B1, C0 plus A0, B2, C1. So we obtain A square C plus 2 AB plus B square C. Okay. So So we can say the following. So that we have this property that this polynomial so is the is, let's say, the unique polynomial such which satisfy the following properties. So the first properties is that so if I consider three diagrams which coincide outside the disk and inside the disk, they differ as follows. Then we have this property. Second, if I consider a diagram D and with a disjoint circle, then you just see like this, and for the circle is 1. Okay, let us check these properties. Okay. So for the property 1.
What precisely do you mean with the first statement?
For the first statement, so let me explain. So let D be a diagram, be a link diagram, and you consider a crossing, let's call it C, of D. So inside D, you have the crossing C. And then you consider, you define D A to be this link diagram. It coincides with D outside the disk, and inside the disk it is like this. And dB is this one. So 1 means that D is A dA plus B dB. Okay? That's what means property 1. So how do we check this? Well, it's quite clear. So we recall the definition. So D is the sum of on the state of D of A alpha S, B beta S, C gamma S minus 1. So we can split this sum into two sums. So the first are the states of D, such that for the crossing, the value is A. Plus the sum on the state of D whose value at C is B. Okay. Now, if you have a state of the diagram dA and you obtain a state for the diagram D by imposing that the value at the crossing is A. So this sum here, the first sum is just the sum on the state of dA of what? A alpha S prime plus 1, B beta S prime C gamma S prime minus 1. Okay. Plus the sum of, let's say, on the state of the diagram dB no B beta S prime plus 1 C S prime minus 1. So this is clear. And when you look at the definition, this is exactly A dA plus B dB. So let us check quickly the second property. So clearly, so this state of the disjoint of D and the circle are in bijection with these states of D. And also, if S is a state of the disjoint union of D and the circle, and S prime is the corresponding state of D, what can we say? So the first bijection comes from the fact that the crossing of D disjoint union to circle are the crossing of D. So it's clear. So what can we? How do we compare this number? They are the same. No, for the crossing in state B, of course, they are the same also. And now, what are the number of circles when you have split the crossings? How gamma S is gamma S prime plus 1. And we conclude. So we conclude this. When you come back to the definition, conclude this. Okay. So finally, for this circle, how many states has the circle? Only one? Huh? So this is a map from the set of crossing. There is no crossing, so this is an empty set. So there is only one map like this. And for this state, of course, there is no crossing in state A or B. And the number of circles is 1. And consequently, what you obtain is for the circle, it is A0, B0, C0 is 1. Okay. So, finally, the uniqueness of this polynomial follows from the fact that if we split the crossing using 1 and then use 2 and 3 to compute D. So it is easy to check that we recover the original definition. So the very first definition of the polynomial. Okay. Thus, we have proved this property. So we have defined a polynomial in 3 variables. So we have associated the polynomial in 3 variables to any link diagram, which is invariant under plane isotopies. So to obtain an isotopy invariant of links, we need to study the behavior of this polynomial under Reidemaster moves. Okay, maybe I recall that two links are isotopic if and only if their diagrams are related by a finite sequence of plane isotopies and Reidemaster moves. So R1, so we have R2 and R3. Okay. So if we want to define an invariant of links, one way is to define an invariant of link diagrams, which is invariant under plane isotopies and Reidemaster move. So we have here an invariant of link diagram. We have associated a polynomial to link diagrams, which is invariant under plane isotopies. So we need to look of its behavior under this Reidemaster move. So let us investigate further move 2. So behavior of D under Riedemaster move 2. Okay. So if we consider so we compute the polynomial for a diagram like this. So if I apply the property 1 from this crossing, what do I obtain? So I obtain, so it is A like this. Plus B like this. Now, next, I apply the first property to the second crossing. What do we obtain?
Sorry, the third move, is it correct?
Oh, yeah. Yeah, of course. You just slide the crossing under or over one other string. Okay, now, next we apply the property 1 to this crossing. So what do we obtain? A. So plus B and next, again, we apply property 1 to this crossing, so we obtain A. So plus B so this by the property 2 is equal to C times this. And so what we obtain is, so A square plus ABC plus B square times the polynomial of this plus well, AB okay. So what is the conclusion here? Tells that this polynomial is invariant under the second Riedemaster move if and only if so A square plus ABC plus B square is 0 and AB is 1. So we can rewrite this as B is A inverse and C, so AB is 1, so C is minus A square minus A minus 2. Okay, so if you want to have an invariant, we need to impose this relation. So from now, so we impose these conditions. Okay, so what does it mean? So we can define the bracket polynomial of a link diagram D this is the Laurent polynomial which belong in the A inverse determined by the following conditions. So first condition, again, we have so are the same as before, but replacing B by A inverse. And replacing C with minus A square minus N. Insert. We have, for the circle, it's just one. Okay. So by what we have done before, we know that this Laurent polynomial is invariant under plane isotopies and Reidemeister 2. Okay, now let us see what is the behavior of under R3. So actually it is also invariant under R3. So let us prove this. Okay, so let us consider so we consider diagram. So inside a disk there is this. Now if we apply the property 1 to the first crossing here, so what do we obtain? So we obtain A plus A inverse okay. Now what can I do? I can apply Reidemeister 2 here. and I obtain this. Okay. I just use Reidemeister invariance under the second Reidemeister move here. Again, I can use the invariance under the second Reidemeister move here to slide this here. Plus A inverse and then using 1 I obtain this. If I use the property 1 to this crossing, I obtain this relation. Okay. So this proves the invariance under the third Reidemeister move. Okay. It remains to study Reidemeister move 1. Okay. So, what is the behavior of the bracket polynomial under the first Reidemeister move? Okay. So we look at this. So we apply 1 to the crossing. So what it is A plus A inverse now here I can apply 2 to this one is just now if I apply 2 it's A inverse minus A squared minus I minus 2. Okay. And so what we obtain is, so A minus A minus A, sorry, so minus A minus 2. And if we look at the other one, what you obtain is just with the other sign, so minus A cubed. Well, this is the same computation. Okay. So what is the conclusion? So this, unless A cubed is -1, the bracket polynomial is not invariant under the first Reidemeister move. So we do not have yet an isotopy invariant of links. So we will modify the bracket polynomial by the so-called Rice number to obtain an isotopy invariance, not of link, but of oriented links. Okay. So we will do this after the break. Okay. Now I will define what is the rise number. Okay. So it is defined as follows. So the rise number. So the rise number of an oriented link diagram D is just the sum of the signs of the crossings. And we denote it WD. This is the sum C on crossings of, and I recall we have this, well, a positive crossing is this, so here epsilon is 1, and a negative crossing is this one. Okay, so just for example. So here the crossing number is 0. For this one, it is. So if I take the other one, for this one we have 1. Now let's take. If I take this one. Here the rise number is, we have 2 positive crossing 2, but if I change here the orientation of one component, for example this one, so here is negative 2. So definition is quite clear. NCCR. This number, the rise number, is clearly invariant under plane isotopies. This is clear. And under the Raidemaster move 2 and 3. And let's call the oriented version. So I recall what are the oriented version of the Raidemaster move. So to consider this one. So, and also there is another one, let's say, with this orientation, and so this is oriented R2, and for R3 you just need to consider the case where all these strands are oriented downwards. Okay. So the invariance is here is clear because this crossing is positive, this one is negative. No, the inverse. This is negative, this is positive. This one is positive, this is negative. So this one is +1, -1. Okay. So this in every case, the rise number does not change. It's quite evident here. And what is the behavior of the rise number under the oriented version of the Reidemaster move 1. So what do we have? So there is two versions, so this one. So clearly we have this relation. So here the crossing is negative, so and for the other version, it is okay. So the rise number change for Reidemaster move 1 as follows. So this allows us to define an isotopy invariant as follows. Let us call it the Kaufman polynomial. So I think this 3. Okay. So if you have an oriented link L, we define KL of A is negative A cube minus D. So this is a Laurent polynomial in A inverse. Well, here D is an oriented diagram of the link L, of the oriented link L. And this diagram D is the unoriented link diagram which is obtained from D by forgetting the orientation of all components. Okay. So this is just a definition, and the main properties is the following. Okay. Is that this is an isotopy invariant of oriented link. So okay, so let us check this. So we need to check. So for an oriented link diagram D, we define this quantity by the right hand side. So we need to check that this polynomial, this Laurent polynomial, is invariant under plane isotopy and oriented Reidemaster moves. So AD is invariant under plane isotopies and oriented R2 and R3. And why? Because the rise number and the bracket polynomial are invariant under plane isotopy and Reidemeister move 2 and 3. So we have already shown this. Okay. Next, we need to check the invariance under R1. So, what do we obtain if we compute this? So, by definition, it is so minus a cube minus the right number of this times the bracket polynomial of this. So here, we already compute this. So it is a cube minus. So here the crossing is negative, so plus 1. And we already compute the relation this. So presumably, we obtain minus 3. So we obtain this, which is the k of this. And similarly, with the other orientation. And so we obtain that this is invariant under the oriented version of R1. Okay. So we finally have constructed an isotopy invariant of oriented links. We are almost done to define the Jones polynomial, but we need the following property. So, actually, a priori, the Kaufmann polynomial is a Laurent polynomial in the variable A. In fact, it is a Laurent polynomial in the variable A square. Okay. So let us show this. So we first prove that if D is a link diagram with n crossings, then the bracket polynomial belongs to what? So either z of a square the Laurent polynomial in A square if n is even, n is A, it belongs to A z of A square. If n is odd. Okay, let us check this. Okay. So let us look at the case where there is no crossing. So clearly, D is isotopic to the disjoint union of circle. And so if you use property 2 and 3, we obtain that D is what? Minus A square minus A is to the M minus 1, which is indeed a Laurent polynomial in A square. So, what are the possibilities when there is one crossing? Up to isotopy, what are the link diagrams with one crossing? So, if you just want one crossing, so up to isotopy, we have this. Or with opposite crossing. Plus the disjoint union of circles. Now, what is the Laurent polynomial in the bracket polynomial for this? So we compute for this, and we found, I do not remember, but maybe minus A cube, I don't know, plus or minus 1. Let's say this minus A cube. Is it plus or minus 3? I do not remember.
It's plus.
Plus, okay. And for this, we obtain. So this follows from the, we have already studied the behavior of the bracket polynomial under R1. And thus, what do we obtain? That the bracket polynomial is minus A plus or minus 3 times what? So minus A square minus 1 minus 2 to the k. And it is indeed, so n is odd, it is indeed in this set. It is 8 times the Laurent polynomial in A square. Now let us explore the case where n is greater than 2. So D has at least 2 crossings. And so we can apply. So we have 2 crossings in the diagram of D. So we can apply relation 1. from to this crossing. So we obtain A with A inverse. So here does not change. Does not change. Here we have. And next we apply again the relation 1 to the crossing here. So we have A with A inverse. With A inverse. A. Okay, so here, so this was like this. Okay. And so this is just A square. The Laurent polynomial, the bracket polynomial of this diagram, plus the Laurent polynomial of this one, plus the Laurent polynomial of this one, plus I minus 2, the Laurent polynomial of this one. Okay, but what can we see? This diagram what are they? Are they? They are link diagrams.
Sorry, the third one is the same as the fourth.
Yeah, no, this is one. Okay, thanks. So these are link diagrams with what? N minus 2 crossings. So here we can make an induction. So if they have 0 crossings, so a diagram with 2 crossings is indeed a Laurent polynomial in A square, so, and so on and so on. We conclude by induction. On N. Okay. So the Laurent polynomial, the bracket polynomial, we know where it belongs depending on the number of crossings. So next, let us deduce the property of the Kaufmann polynomial. So let L be an oriented link and D. Okay. So we consider a diagram D of L. And we denote by L and be the number of crossings on the diagram D. So what can we say? First case, so if N is odd, what could you say on the right number? The rise number is the sum of the sign of the crossing. So it is a sum of plus or minus 1. So a sum of an odd number of plus or minus 1 is odd. Okay. It's odd. And so K of D, it is minus A cubed minus so this, since omega D is odd, this belongs to a Z of A square. So this is the conclusion of before. So this is clear because omega D is odd. By before, this belongs also to A Z of A square A minus square. And so their product is a Laurent polynomial in A square. So, and if n is even, then the rise number is even. And so this belongs by this omega D is even, this is in Z A square A minus 2. And by the previous properties, this is again in Z A square. So we also obtain a Laurent polynomial in A square. Okay, so actually then we have shown the property that the Kaufmann polynomial is a Laurent polynomial in A square. And so we now define the Jones polynomial just a renormalization of the Kaufmann polynomial, but we call it, but it was previously defined using other method. That's why we have the name. So Jones polynomial. Okay. So the Jones polynomial of an oriented link L is the Laurent polynomial in the variable T1 half defined by V of T is just the Kaufmann polynomial of L. So this is a Laurent polynomial in A square, but here A square is T minus. So this is a Laurent polynomial T1 half. Okay. So just remark that here T1 half is the variable. It's square T1 half square. We just denoted by T is denoted by T. And actually, and we should write VLT1 square instead of VLT. But it is traditional to have this notation. And for knots, so link with one component, actually it is a Laurent polynomial in T. We will see this later. Okay. Okay. And so, what's this theorem? So, of course, since Kaufman polynomial is an isotopy invariant, so is Jones polynomial. But it satisfies the following relations. Let's say. So, oriented links. So it is an isotopy invariant of oriented links such that, first, so if L plus L minus L0 are oriented links which are the same except inside the tribal, where they are as so. So you consider a tribal so you have the same link. So in the three space, and inside outside the three balls they are the same, and inside they are as follow. So this is L plus L minus and L0. Okay. So if we are training like this, then we have this so-called skein relation. So VLT minus T. So here L plus VL minus of T is equal to T1 half minus T minus 1 half VL0 of T. Okay. So the Jones polynomial satisfies this skein relation. And the second, so B, V, if I take L disjunctional with the oriented knot, it just minus T 1 half minus T minus 1 half VL of T and C for the handling and not we have 1. Okay. And okay. And moreover, the Jones polynomial is actually in the unique isotopy invariant of oriented links which satisfy A and C. Maybe I should have some other properties here. Also, if the number of components of L is odd, then the Jones polynomial is a Laurent polynomial in T. And for example, this is the case for knot. They have one component. And if the number of components of L is even, then the Jones polynomial is actually T1/2 times a Laurent polynomial in T. And that's why we denote it by VL of T instead of VL of T1/2. Okay.
Can I ask, is there some reason why is it called V instead of J?
Yeah, because the first name of Jones is Vaughan. Vaughan, je sais pas. Vaughan, V-A-U, Jones. But sometimes in the literature you will find J instead of V. Okay. Probably I have no time here to prove this theorem, but let us end by computing the Jones polynomial of the trefoil. Okay. So let us consider this trefoil T. And of course we take an orientation, this oriented trefoil. Okay. So we need to consider, so we use property A to this, for example, this crossing. So this crossing, this is like this. If we consider this crossing is +1. Maybe take another color. Maybe red is better. So I consider this crossing here. So it is positive crossing. So I can resolve it in two ways. If I take a negative crossing, I have this one. So it becomes negative crossing. And if I use 0, if I smooth it, I obtain this. Okay. So what do you think of this link? This link is just the unlink. This is here the oriented uplink like this. Let's call it H. Okay. Now I can also, so here we have, if I take here, we have a positive crossing. So I have two ways. So here, if I change to this, I obtain so this is the unlink with two components. And if I smooth the crossing, I will obtain this way. Okay. And this is isotopic to the unlink. Okay. So now we can apply A. So by C, the Jones polynomial of the unknown is 1. And by, if I apply B, the Jones polynomial of the two component unlink is just minus t 1/2 minus t minus 1/2 this V of the unlink, which is 1. Now, if I let's call this crossing, let's here C0 and here C1. By A applied to C1, what do we obtain? T inverse V of the uplink minus T V of the two component unlink is T 1/2 minus T minus 1/2 V of the unlink. So you obtain that V of H is T times T square times T 1/2 plus T minus 1/2 plus T 1/2 is T minus 1/2. So of course, check my computation. So minus T5 half plus T3 half plus T1 half plus T. Okay. And finally, if we again apply the skein relation A to the crossing C1, to the crossing, I call it C0. What do we have? So T times the just polynomial of the triform, so T inverse minus T V of the one component is T1 half is T minus 1 half V of H. And what you obtain is that the Jones polynomial of the threefold is, so I don't want to make the computation, I don't know. So, yeah. Minus, so plus minus T4 plus T3 plus T. Or maybe I made some error here. So just okay. What I found here is minus T1 half T square minus 1. Just check the computation. This is easy computation. Okay, so here you have a way to compute the Jones polynomial inductively. Okay, maybe I stop here. So I will put by Monday the exercise sheet concerning the Jones polynomial on Camilo. So you can upload it to prepare the next the exercise session. Okay. So next time, so we will prove the theorem, and we will define the Jones polynomial by other means. So using quantum groups, UQSL2. So do you know a little about algebras and their representations? Or not, who does not know anything about algebra and their representation? About algebra over a field and representation. Do you know the definition of? If I ask you, do you know how to define an algebra over a field by generator and relations? This kind of things. Do you know this? Okay. And do you know what is a coalgebra? Yeah. And do you know what is a off algebra? Or by algebra? Okay, so I will define this next time.